Hello all, welcome back to my YouTube channel all about VLSI. In our previous videos, we have seen how to how exactly Sobel Edge Detection is working with some examples, and we have seen and also we have just discussed the basic prerequisites like what do you mean by image, what do you mean by pixels, and what do you mean by kernel and all. And after that, we have seen how we are going to actually perform Sobel Edge Detection and how exactly we are basically trying to find it out the edge is being detected or not, right? Now, in this particular video, we are trying to discuss how we are going to develop the Verilog code for Sobel edge detection. So for that, we have took a Verilog code. Now, first of all, the purpose of this particular code is to read the RGB image from the external memory. And that particular from the external memory, we are going to read it to our particular file via some Verilog keyword, which is known as $read memh, right? Now, each then after each particular pixel is this particular RGB image is converted into grayscale, okay, using ITUR BT 6.01 Luma approximation. What do I mean by this? I will explain you. Now, after that, we are going to apply 3 cross 3 Sobel operator for detecting the edges, right? Now, then the magnitude is thresholded to produce a binary edge map stored in a separate output memory. So that is what we are going to perform. Okay. So the first step is we are going to convert. We are going to first of all read the external memory into our Verilog file, and then we are going to convert the color image into grayscale image. Why are we converting this? We have already discussed in our previous session. Next, we are going to perform Sobel edge operation, Sobel operator, and then we are going to basically compare with the threshold, right? Now, let's have the look into our memory layout, like whatever the memory we are going to have, which was basically storing a color image that is going to have each pixel of a 24-bit width, where 23 down to 16 is red and 15 down to 8 is green and 7 down to 0 is black. Okay, so what exactly I mean by this, let me show you with this example. Let's say if I'm going to have a particular image, let me show you over here. Yeah. So let's say if I'm going to have a color image, so that particular color image is being stored inside my array. Like the first memory location, mem of 0 is going to have a 24-bit pixel. Since it's a color image, the width of each particular pixel is 24-bit, right? And next, the first location will be having another 24-bit width pixel. And next, the second location will be having another 24-bit pixel, right? So this is how this particular pixel color RGB image information is being stored inside my memory. Now, generally, if we are going to mention our color image, we are going to mention it with three dimensions, right? One is R plane, and another is G plane, and another is blue plane, right? So where R plane is going to have the pixel informations of red, and G plane is going to have the pixel informations of green, and plane is going to have the pixel informations of blue, right? So each of width 8 and 8 times 3 is 24. So combined information is being stored inside our memory already in the external memory, and from this external memory we are going to read 24-bit pixel data, and we are going to store it inside our Verilog code. That is what we are going to do, right? Now, next, after that, we are basically going to store that pixel information in row measured order, and the address of each particular pixel is basically decided by row into image width plus column. What do I mean by this? Let me show you now. Now, let's say this is my address 0, right? Now, this is my address 0, and okay, let's discuss this later in later slides. What do I mean by this address calculation and all, right? Now, next is image width. So image width is 8. I mean 8 bits. That is 1 pixel per row, right? So and image height is number of rows, which is by default 8, and threshold is Sobel magnitude for basically edge detection. And we are going to basically read this file image underscore RGB, which is an hexadecimal file, and we are going to read it via this read memh. And output of the edge detection, we are going to store it in a memory, which is edge underscore mem. So this is the synopsis of what are we going to do, and let's discuss them in great detail exactly in our upcoming slides, right? Now I've declared a model which is Sobel Edge detector where image width is 8 and image height is 8 and threshold is 30. And basically this is just for sampling purpose, and your actual image will be having more width and more height. Okay. Now, and I've also declared clock, active or reset, and start is basically for starting the process, and done is basically to indicate that this entire process has been completed. Now, for knowing exactly how many pixels I'm going to have in my image, I'm going to use a formula which is known as image width into image height will give me exactly how many pixels are there. Basically, image width is over here 8 and image height is 8. So total number of pixels is 64 in this particular case. And address width will be decided using this dollar C log 2, which is basically going to perform the log operation on this total pixels, which is log base 2 of 64, which is 8. So here address width is basically 8. Now, over here, I'm going to declare a memory basically for storing my, the color image, right? So how I'm going to read my color image, I will show you. For storing this particular 24-bit RGB input image from the hexa file, I'm going to declare an register file of 24-bit width. Why it is 24-bit width? Because each particular pixel is of 24-bit. And total how many pixels are there? It is decided by width and height of your image, which is basically 64. So I'm going to have total 64 number of locations. So I'm going to have total 64 number of pixels which are being stored inside this input underscore mem, and each pixel is of 24-bit width. Right now, next after that, we already know that particular pixel in your grayscale is going to have only 8-bit width. Each pixel is only going to have 8-bit width in the case of your grayscale image, and this we have already discussed in our previous sessions. And in the case of your color image, your pixel is going to have 24-bit width. Each particular pixel is going to have 24-bit width. Right now, here, since it's a grayscale image, I'm going to declare it as of 8-bit. Each particular pixel is of width 8-bit, and total number of pixels are the same. We are not going to reduce the total number of pixels. Those will be 64-bit only, but we are going to basically reduce the size which we are going to define a particular pixel. In the grayscale, it is only 8-bit. Right now, after performing Sobel Edge detection, our final output will be only 1-bit, and which is basically which I'm going to store in my edge underscore mem. And the total number of pixels is again the same, 0 to total number of pixels, which is 64. Right now, these are the internal memory arrays which we have declared over here. Now I'm going to have few states over here basically for FSM processing. One is idle state and another is loading for loading the data from the output memory. And next is grayscale for basically converting my color image into gray image. And next is Sobel for for performing Sobel convolution, and dumping like for writing the result into my output memory, which is edge underscore memory, and done state for indicating the done status, right? Now I'm going to have a particular variable which is known as state. Now I took over here few internal variables for counting purpose. One is pixel counting, and another is row counting, and another is column counting. Now after that, we have also took few variables for storing red value, green value, and blue value, and gray underscore full is what the gray image will be stored inside it, and it is of width 18-bit. Right now, what is it exactly? We will understand. We will try to understand what is exactly happening. And also here we have declared a few registers of 8 down to 0, which is basically 9-bit. So the last bit is basically for storing the sign, because when we are going to perform Sobel edge operation, Sobel convolution, we are going to get the results in negative numbers also, right? So P00, P01, P02, P10, P12, P20, P21, P22 we are going to have, and the center pixel we are not going to consider. So this particular center pixel across only we are going to perform the Sobel edge operation, right? And this is a formula we are going to use for finding out the gradients in the horizontal direction and the vertical direction. So horizontal direction, the gradient formula is P02 plus 2P12 plus P22, right hand side pixel values added minus left hand side pixel values. So this will give me the horizontal gradient change, and the vertical gradient change will be given by downward pixel values minus upward pixel values will be given, right? For example, let's say if I'm going to have this particular pixel, which is let's say if I'm going to have this kind of pixel information just for analysis purpose, I'm taking this particular pixel information with me. Now, let's say if I want to perform the kernel, the Sobel operation uh, using on this particular image, right? So I'm going to have a 3 cross 3 kernel that we have already discussed previously, which will be having in the gradient direction, and in the gradient in the horizontal direction, and gradient in the vertical direction, right? Now, since it's a 3 cross 3 kernel, we are going to have, let's say if I'm going to have this particular pixel, we are basically starting the operation from this particular edge. And let's say if we are over here, then we are basically finding out the neighboring pixels of this particular phi. And then we are going to perform the gradient, horizontal gradient and vertical gradient across this particular pixels. Okay, this is the basic idea which I wanted to give. In great detail, we are going to discuss in the next slides, right? So for this, I have declared this. And next is I have declared a 12-bit GX and GY. Okay. And the absolute value of this, because we are not going to consider the negative values, we are going to make them positive. And the magnitude, basically root square of GX square plus GY, right? So these are the things which we have declared as of now, right? Now, let's move towards our FSM state. So if and I've also declared one integer variable basically for counting purpose in the for loops, right? And within an always at the rate percentage of clock, if reset is done, I'm basically initializing everything like state, pixel count, row count, and column count, and done. Now, if I'm in my ideal state and if start is given, then I'm going to a state which is known as load state. Else, I'm going to stay in the same state. You can write this particular condition, or else not an issue because you have initialized all the things. So no latch will be forming over here. Now, we are basically going to, if our start is equal to 1, we are going to a state which is known as load state. Now, what is happening in the s underscore load state is we are trying to read the pixel information from image underscore RGB and RGB.hex file, where our actual image information is stored in the binary format, in the hexadecimal format. Now, that we are going to read it into the array which is known as input underscore mem. Now, input underscore mem we have declared over here, if you have remembered previously, yes. This is basically going to store the color information, which is of each pixel is of width 24-bit, and we are going to have total 64 number of locations, right? So like this, we are going to have input underscore mem. So we are going to have input underscore mem. In the first location, we are going to have first pixel information, which will be of 24-bit width. And in the second location, we are going to have input underscore mem of 1 will be having the second pixel information, which will be again 24-bit width. Like this, we are going to have 64 number of pixels. Each pixel is of 24-bit width because each pixel is a color image. Now, in this 24-bit information, as I've told you previously, one such slice like from 24 down to, let me show you this particular thing. Where is it? Yeah, 23 down to 16 is red information, and 15 down to 8 is green, and 7 down to 0 is blue. So in this particular memory, 23 down to 16 is red, which is 8-bit for red, and 15 down to 8 is for green, and 7 down to 0 is for blue. So like this, in each particular location, again the pixel information is classified into RGB, right? Now, so we have stored that particular information inside this memory, which is input underscore mem. And we are initializing this particular variable pix underscore count is equal to 0, and we are going to state underscore gray. Now, in this particular gray state, what are we trying to do is we are trying to extract red value, green value, and blue value. Now, how are we exactly extracting it? So our value is equal to input underscore mem. Pix count is initially 0. So input underscore mem of 0, 23 down to 16. In G value is equal to input underscore mem of 0, 15 down to 8. And blue value is equal to input underscore mem 0 of 7 down to 0. So what do I mean by this? So here r underscore value is equal to this particular memory. First, we are trying to access the first location. First location is basically 0. And in this first location, we are trying to access 23 down to 16. And again, G value is equal to, again, the first location input underscore mem. First location is 0. Next is 15 down to 8. Next, blue value is basically input underscore mem. First location 7 down to 0. So like this, we are trying to access the R value, G value, B value from the first location. We are trying to slice this vector, and we are trying to store it in our three different variables R, G, and B. Now, after that, we are trying to basically convert this particular R value, G value color image into gray image. Now, how exactly we are trying to perform the gray to binary information is basically, if I want to perform binary, color to gray. So this is the formula which I'm going to use. So what is that formula is color to gray. If I want to perform, what is the formula is R plus G plus B divided by 3. Just I need to take the average. That is as simple as it. But over here, we are also adding few weights to this R, G, and B. So that's the reason I'm basically adding few weights. For R, I'm going to add 306, and for G, I'm going to add 601, and for blue, I'm going to add 117. So these are the standard weights which we are going to add. And since and here G is green is more more attractive to our eyes. So that's the reason I'm going to have more weight to this particular variable, right? Now I've added few weights to this particular R, G, and B, right? Now basically I'm after adding them, and what I'm going to do is I'm basically trying to store it inside the variable which is gray underscore full, right? Now over here I'm trying to basically after adding them, and give me a second, one second. And over here, yes, so this is the thing which I was explaining previously. So our human eyes are more sensitive to green and less sensitive to red and least sensitive to blue. So grayscale, we can actually perform R plus G plus B by 3, but instead we are going to have weighted coefficients that are being used. So this is the actual formula which we are going to use, which is a standard formula for conversion from color to gray, where 0.299 into R plus 0.587 into green and plus 0.114 into B, right? Where Y is nothing but our grayscale, and R is red component, and G is green component, and blue is blue component. B is blue component. Now, why are we, multiplying it with 306, 601, and 117? Because, so if you can see, the floating point numbers are very expensive in our hardware. You're going to have a lot of hardware. So instead of using 0.299, 0.587, 0.114, we are going to scale them by 1024. So this 0.299 into 1024, if I'm going to multiply, I'm going to get 306. And if I multiply 0.587 into 1024, I'm going to get 601. And 0.114, if I'm going to get multiplied by 1024, I'm going to get 117. So that's the reason I'm going to multiply 306 into R, 601 into G, 117 into B divided by 1024. I'm going to get the same thing, right? Now, so multiplied over here, but how we are going to divide that, we are going to see in the later sessions, right? So yeah, okay, we will discuss it over here only. So after multiplying it, how we are going to divide? We are going to basically right shift by 10, because 1024 is nothing but 2 power 10. So gray is equal to gray underscore full. Right shift by 10 will basically give you the division result. That's it. So this is how we are going to perform the division in our coding. Now over here, let's discuss this. Where is this gray underscore full? Yeah. So we have basically multiplied and we have stored over here. And still we are talking about the first location pixel only. We haven't started with the other pixel locations. We are in first location itself, right? Now we are basically checking pixel count is greater than 0 or not. No, it is not greater. So what are we going? We are going to skip this, and pixel count is total number of pixels. No, still we haven't reached this. Okay. Then we are basically incrementing it. Pixel count is equal to pixel count plus 1. Now what is going to happen? We are iterating to the next location. So up to now we have discussed why the values are multiplied by this particular specific numbers, then what are we going to do? Since pixel count is not greater than 0, we are incrementing it. So we are basically going to increment the pixel count so that this particular value will become r underscore value is equal to input underscore mem, and pixel count will now be equal to 1. That means I'm going to first location. And again, 23 down to 16. And input underscore mem, 1 of 15 down to 8. And 2 of 7 down to 0. So like this, I'm basically uh, having the first location pixel information. So from this code, I'm incrementing it. So you can see pixel count has been incremented. Again, I will be in the same state only. I'm not going to any other state. And here pixel count has been incremented. That means input my first location. I'm again extracting R value, G value, and B value. Then I'm multiplying from this and I'm basically storing inside my gray. And next, I'm basically checking for my pixel count is greater than 0 or not. If it is greater than 0, then what is that I'm going to do? Yeah, now it is pixel count is greater than 0. So gray underscore full of 17 down to 10. So gray underscore full 17 down to 10. This particular information, what I'm going to do is, and now let's try to understand like exactly what's the reason it is 17 down to 10 over here. Now, if you carefully observe, so let's say if I'm going to calculate my gray value using 0.299 into R plus 0.57 into G and 0.114 into B, this was a standard weights which we were adding as a coefficients, right? For example, if my R value is 100 and G value is 150 and blue value is 200, then my gray value I'm going to get is 140.75, which is approximately 141. Now, when we are dealing it in hardware, so instead of preferring floating numbers, we what we have done is we have multiplied everything, every pixel value 0.299, 0.587, 0.114 into 1024, and we had got a new value. Using this value, we were multiplying our R, G, and B, and we are adding them so that we are going to get gray underscore full. This we have already seen. Now, what is this gray underscore full actually containing? It is containing 306 into 100. With our example, if we see 300 into 6 into 100 plus 601 into 150 plus 117 into 200, which is approximately 144, 150. This is our G value, right? But our expected value is 141. But what are we getting? We are getting 144,150. Why this much large value? Because we are basically multiplying gray into 1024. Okay, so which is 141 into 1024, which is nothing but 144384. Now, so that's the reason, which is very close to 144150. So difference due to the coefficient property. So what are we going to do? So gray full is nothing but grayscale value into 1024. Now, how are we going to get it back our real grayscale value? We can either divide 144,150 divided by 1024, which is approximately 140.77, which is nothing but my 141 or 140 depending upon my rounding, right? Now, instead of actually dividing it, what I can do, I can basically right shift by 10. This I've already shown. Now, instead of that, what we can do is we can basically consider the bits from 17 down to 10. So where the 17 down to 10 represent the actual integer part and 9 down to 0 represent my fractional part. So because we scaled this particular value by 2 power 10 or 1024, so the lower 10 bits represent the fractional part. So that's the reason we are, so you can see this particular thing. So when you select 17 down to 10, you're simply throwing the away the last 10 fractional parts, or you're basically performing this particular part. So that's the reason we are only selecting 17 down to 10. So you can see in this particular code, we have only selected 17 down to 10 and we have stored inside my gray underscore mem. That is my only integer part. And after that, what I'm going to check it, I'm basically checking whether my pixel count is reached the total pixels or not. No, it has not reached because total pixels is 64, right? So that's the reason I'm again incrementing my pixel count, and I'm going to next location. I'm going to extract it. I'm going to multiply it. I'm going to convert it into gray. And from that, I'm going to scale it. After scaling, I'm going to basically, store it inside my gray underscore mem, and again checking for my pixel count. If this pixel count is reached to 64, then I'm basically storing all the particular gray full image, the last pixel value into my gray underscore mem, and I'm going to make sure this row underscore count is equal to 0 and column underscore count is equal to 0. And I'm going to a state which is known as Sobel. Now, in this Sobel state, the actual kernel operation is going to perform that we are going to discuss in our next video. And up to now, what we have discussed, we have seen how a color image is being converted into grayscale image by scaling factor. We are going to scale and all, right? Yes. So I have tried my level best to explain this concept in great detail. So if you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.